Wow. All right. We have already got a bunch of people joining us, at least one from Portugal. Welcome to the Golden Path to Spring One. My name is Deshaun Carter. I'm a Spring Developer Advocate. And joining me today, Paul Baker from Netflix. Paul, why don't you introduce yourself?
Sure. My name is Paul. I work at the Java platform team at Netflix. And today we're going to talk about how we actually use Java today.
Wonderful. This is exciting. I think a lot of us know the story about Netflix and how it's done amazing things for this whole cloud native movement. And we're going to allow questions. We're going to have questions. Ask your questions in the chat. We'll get to them as soon as possible. I'll kind of help manage the questions. But with that, welcome. I'm going to turn it over to you. Are you ready?
Awesome. Yes, I am.
All right.
All right. Thanks. So we are going to take a look at how Netflix is really using Java today. And the emphasis here is today because things have really changed over the years. If you have paid attention to our tech blogs and maybe conferences, etc., you might really have the idea that Netflix is all about RX Java microservices, and there's Hystrix and Spring Cloud everywhere, and really Chaos monkeys are running the show here. Well, there's some truth of that, and definitely there was some truth to that. But today we're also just going to bust some myths here. Things have changed drastically over the years. Our architecture has evolved multiple times. That also means our tech stack has evolved. And technologies that we might have been using several years ago might not have been the technologies that we're using today. So we are going to take a look at how that architecture evolved and what it means for our tech stack, and specifically how we use Java. So my name is Paul. I'm in the Java platform team at Netflix. I do a lot of work around Spring Boot and kind of the Netflix flavor that we put on top of Spring Boot. I'm also a Java champion, and I published 2 books about Java modularity. Those books are a little bit dated right now, but that's kind of what I did a while ago. You might also know me from the DGS framework. I was one of the original authors of this framework, and this is the GraphQL framework that we use at Netflix to build GraphQL services. And later on, we will talk quite a bit more about GraphQL and how we use that today. Right, so let's dive into this tech stack. But before we do so, we have to understand how our architecture has been evolving, and that obviously impacts the way how we use Java and how we use other tools and libraries. So let's take a look how this architecture is always evolving. And specifically, we're going to take a look at what we call the LOLOMO, the list of movies. And of course, this is the screen that you're probably all familiar with if you've used Netflix. Basically, you have a list of lists. So we have a list like recently added, which is then a list of movies. So this is probably something you're familiar with, and this is, of course, a very important part of our system and our architecture. You should also understand that there's also many other parts of systems and applications that we have at Netflix. For example, we have built a lot of tools and applications in the studio space, so the space where we actually produce shows. And very often these are more traditional enterprise apps, as you might be more familiar with. But today we're going to talk about the architecture that is behind all the kind of the streaming systems. So we start about 6 years ago. This is right around the time that I joined Netflix. And kind of the architecture that we had in place to serve streaming at that time is what I call the Groovy era. Now, there's a bunch of things in this picture that I need to talk about. First of all, on the right-hand side of the slide, you see that we have many different microservices. And this is really just a simplified view of it. But there might be a microservice that's responsible for the top 10 shows. And another microservice that actually contains the movie metadata, so the movie titles and some blurbs about the show. That might be the movie service. And then we need the artwork for a service, like the thumbnails that we show in those lists of lists. And that might be the artwork service. And then maybe we have the LOLOMO service itself that kind of figures out, okay, these are the lists that we need to render. Now, all these different microservices are important to render this one screen. Now, just imagine that we would have a device, let's say a TV, and this TV would have to connect to those different microservices directly. So let's say for this one screen, we need to call 20 different microservices. If we would just call those 20 microservices directly from the TV, that would be extremely inefficient. It would be inefficient from a memory perspective, with overhead of networking. It would not be efficient for like the data that we send over the network. It would also be extremely complex on the UI development side, because now on the UI side, we would have to take care of actually handling with failover, and what if one of these services doesn't respond in time? That would just not be maintainable, essentially. So what we did, we put a API server in between. And the API server is kind of the one thing that the devices care about and what the devices call. So to render this Lolemo screen, a device would do one network call to the API server. Now, the other thing that is important to understand about this is that these devices are all different. The memory constraints and the network constraints for a TV are very different than they are for, let's say, an iOS device, where you might be on mobile data. And again, are very different from the capabilities of a laptop. And another aspect here is that a TV, once you like walk out of the store with a new TV, very often these TVs never get updated anymore. So the software running on these TVs is fairly static. Now, that means that it would not be possible to have like the one API to serve all those different devices. So if you're familiar with writing like a REST API, where you have like one REST API and everyone connects to this one REST API, it doesn't quite work in this context because we can't optimize those endpoints well enough. So what we did is have a capability in the API server where UI developers can actually write a Groovy script. We were kind of big into Groovy at the time. Groovy is obviously a JVM language. And that Groovy script would be responsible for taking the request and then fan out to all the different backend services, to the different microservices. But we're already in the API server, so now we can safely do that fan out in a very optimized way. And what would really happen is that a Groovy script would actually just call a bunch of Java APIs provided by client libraries. And these client libraries are just libraries, Java libraries, that represent those backend services, those microservices. And essentially, it would just wrap like either an HTTP call or a gRPC call, and it was kind of shielded from the Groovy scripts. Now, this architecture actually works really, really well because this, for the last several years, has been kind of the main architecture that all our streaming traffic would go through. And even today, even though we have like newer, evolved versions of this architecture, still a large portion of streaming uses basically this architecture. So it works really well, but it's not perfect. You might also be wondering, if you have been reading about like the Netflix technology stack, is this API server Zool? And it's not. Zool kind of sits in front of this API server, but it really acts as a proxy. That would really be the front door, but it's not really that interesting kind of for the rest of the story, so we just leave that out. But just know Zool is kind of a separate thing that sits in front of this. Now, one really important thing that we've already seen is that we have a massive fan out from those Groovy scripts to all those different client libraries written in Java that then call out remotely to microservices. So we have multiple remote calls. Of course, we need to make some of these calls or most of these calls in parallel, because otherwise it would just be way too much time basically before you would get a response back. Now, if you call out to 20 different microservices or maybe more, it is likely that once in a while, one of those calls will not go very well. Maybe the top 10 service has some performance problem going on and is not responding in like the time that we needed to respond in. Now, for you as a user, it would be a really bad experience if just because the top 10 service has a performance problem, that you can't use the Netflix app, that nothing comes back. That would just be a very poor experience. Instead, it would be much better if we just realize, okay, the top 10 service is just not doing its thing right now, and we're just going to render the Lolemo without the top 10 row. And as a user, you might not even know this because there's like other ways to find the show that you want to be watching. Now, just imagine that you're going to implement this fan-out behavior with fallbacks with just plain Java threads, right? Because we want to work in parallel, so we're just deeply into threading territory here. Just imagine how you would implement this. You would probably create a thread pool, and then that's how you fan out. That's pretty easy to do. But now we have to wait for the data to be ready from all those different threads. We have to combine it again. And we also had to think about failover. So what if one of those threads is not giving us data back quickly enough? Well, this becomes actually really complex to do. Working with threads on this kind of level is just really not easy. And you will run into a lot of complexity and most likely in a lot of performance problems. So this is where we really started looking at like reactive programming. And specifically, we started developing RxJava, which was partially developed at Netflix in the early days. And with reactive programming, and RxJava is just one implementation of that, you can basically, in a more functional way, declare that kind of fan-out behavior and also take care of error behavior for fallbacks and all that. And on top of that, we also wrote a tool called Hystrix, which is basically taking care of those patterns around like bulk heading, where if services misbehave, that we can introduce fallback behavior. And it also adds observability to those remote calls. So RxJava really was just like the only tool how we could manage such fan-out behavior in a easy to understand and efficient way. So this was a very critical part of how we did things. It also meant that RxJava as an API kind of leaked everywhere because microservices started using it in its API because, well, it's kind of how they are used anyway. The client libraries were leaking that, and the Groovy scripts were obviously using RxJava. So this reactive style of programming kind of became the norm everywhere. Now, there's also limitations to this architecture, although it works really, really well. First of all, we have a lot of scripts to manage because, as I said, we have an endpoint script in Groovy for each device, basically every screen for each device, and then also every version of each device. So there's up to thousands and thousands of scripts that needs to be running, first of all, in the API server, so they all take memory, just booting up, and they need to be maintained, obviously. Not as important as you might think, but the UI devs generally don't necessarily like programming in Groovy or Java because it's not a primary language that they do their work in. A UI developer for like 90% of their work would work in whatever UI technology they're working in, and then they needed to do a little bit of Groovy on the side to implement those endpoint scripts. And just because it's not their primary focus, it is really hard to be like super familiar with it. Not that big of a deal because obviously these are very capable engineers and it's really not a big deal to just have another language in your toolbox, but there was a little bit of friction there. A bigger problem is that there wasn't really any local development workflow. It was kind of envisioned that, well, these scripts are fairly simple, so there's really no need to kind of deal with them as a normal application. And basically, the only way to debug these things was to upload them to the API server and run them on the API server. Well, the API server itself, you couldn't really run on a laptop because there was just no laptop with enough memory to run the thing because it had to load all those scripts. So that was definitely a big pain point. And then something that we also just learned the hard way is that reactive is really hard. And if I just speak for myself, I've been doing reactive programming for, I don't know, 10, 12 years, and I've been pretty deeply invested in it. And still today, if I look at like a big piece of code written in whatever reactive API it might be written in, so it might be Project Reactor or RxJava, it doesn't really matter. There's that style of API. If I look at a big piece of code like that, I have often like no idea what it's actually doing. And it's actually really hard to kind of parse and understand it in your head. And besides that, this API server, because everything was running in that one JVM, basically, was pretty hard to scale. So we made improvements to this architecture. And instead of using Groovy for those endpoint scripts that would be literally running in the same JVM as the API server, we took those scripts out and we built a platform as a service, basically for node services that we call Node Quark, that would be responsible for that, like that front door. And this is really just the BFF pattern, the backend for front end pattern. So we create a backend specifically for a front end. And these were just, basically just node services. Now, of course, they still need to talk to all those backend services. And the way that happened is the API server was actually using or exposing a Velcore API. And this Velcore API would be kind of the front door for the Node Quark services to talk to the different backends. Now, Velcore is basically very similar to GraphQL. And at the time that Facebook was working on GraphQL, and before it became a public thing, Netflix was kind of doing the same thing in Velcore, and they're based on very similar concepts. So basically, it's a way to it gives you a graph API into your data, and Velcore was the API that was used to talk to all those different client libraries and do the fan out. So the API server itself didn't change that much. We still have a client library representing pretty much every backend service, and maybe it adds some local caching and all that. And it also means that every time something changes in the backend service, they usually have to also produce a new client that then needs to be installed in the API server, and that basically just means loading a new dependency. So that means the API server needs a redeployment. So the API server is still like a huge monolith that is pretty hard to maintain just because the rate of change there. But we did make some improvements because now we have a limited blast radius. If one of the scripts is misbehaving, it only impacts that specific device instead of impacting potentially the JVM that all the scripts run into. That makes it easier to scale. And Node is, let's say, sometimes a better fit for UI teams. You might think that Node is something that every UI developer uses. That's really not the case because there are many other languages that are very relevant for UI development. Think about iOS or think about Android, which is basically Java. So this was like a little bit better than Groovy, but it's not like the best fit for everyone either. Still, we were left with a lot of the same problems, though. We still had a lot of API duplication because if you look at the endpoints for example, Android and iOS, they are really very similar, but they needed to be separate because that's kind of how the whole system was designed. The API server, as I said, is still extremely complex to operate because there's a very high rate of change in the client libraries. And every time there's a updated client library, it needs to be installed into the API server. If you have a high rate of change, it means that once in a while, these changes will be bad. There will be issues introduced. And now someone has to go and investigate these things. And there's still kind of a gap between the UI teams and the backend teams because you have this API server team sitting in the middle that is responsible for creating that Velcore API. They are not really owning the data because that's what the backend teams do, so they don't necessarily know the details of the data. The UI developers, they know exactly what they need, but they don't necessarily know what data might become available. So just having that one team in the middle kind of hinders communication between the backend and the front-end teams. And of course, this is still using reactive APIs because we are still dealing with Velcore, and that was still requiring kind of an RX style of programming. Now we fast forward to today, kind of how we are evolving our architecture now, and this is a much bigger and more exciting change. So right now we're building our architecture on top of GraphQL Federation. Now let's start on the side of the microservices. The microservices now are exposing GraphQL. So it's not just a REST or gRPC endpoint anymore. They're all speaking GraphQL. And it essentially means that they are still responsible for their piece of data, their piece of the API. And what they do is, for their piece of the API, they produce a GraphQL schema into a schema registry. Now, GraphQL Federation is a specification that basically defines how these multiple separate schemas can be put together in one federated schema. So if you look at the Lolemo DGS, it might define a GraphQL schema that introduces a type show. And on the type show, we have a title field, and that's it. That's all it knows. However, the images DGS, which is responsible for like artwork, might also introduce the show type, but it extends the existing show type because it's not the owner of show, but it can add fields to that already existing type. So in this case, it adds a field artwork, which has a URL. Now, both these DGSs, both these GraphQL services, publish their individual schemas to the schema registry. And now from the perspective of a device, they can just run a query where in the query we're asking for, in this case, it's the Lolemo query, and we're asking for titles and artwork URLs. And from the perspective of this device, it doesn't know that this data is coming from different microservices. It just knows that there is a GraphQL schema, and in the GraphQL schema, there's title and artwork URL. And it will just ask for those two specific fields. This query goes to the GraphQL Federated Gateway, and just based on the schema registry, the Federated Gateway knows that it needs to do a call to the Lolemo DGS to fetch the title field, and it needs to do a call to the images DGS to fetch the artwork URLs. The really interesting thing here is that it doesn't have any specific code for those backend services. There is no client library specifically for the Lolemo DGS or the images DGS. This is all completely done on the specification level of the GraphQL schema. So just because the schemas are there, the Federated Gateway knows how to talk to these services. One other thing that we get kind of for free with GraphQL is that with GraphQL, you have to be very specific in your query about what fields you want to get back from a case. We are asking for the Lolemo with title and artwork URL. That's the only data we are getting. Now compare this to a REST call, where on a REST call, we would maybe ask for the Lolemo endpoint, and the service would probably just give us whatever data it has for the Lolemo. And it might be much more data than this device at that point needs. Now, just because GraphQL requires you to be specific about the fields in the data that you want to get back, we don't need those different device-specific endpoints anymore. It is now good enough to have the one giant GraphQL schema to basically serve all those different types of devices. Now, there's some huge benefits here. First of all, as I just said, we don't have API duplication anymore. We don't need those BFF services anymore, those backends for front ends. We just have the GraphQL schema, and that's flexible enough from a UI development perspective. That also means we don't need to do any server-side development for UI engineers anymore. They just care about their UI. Their UI just speaks GraphQL, and there's nothing sitting in between anymore. It also means that both the front-end developers and the back-end developers that own the data, they now have a schema to collaborate on, and they collaborate directly. There is no API server team sitting in between anymore that kind of defines the final API, because all that we're talking about is a GraphQL schema, which is directly produced by the microservices. So now we have a very direct communication path to collaborate on as well between the front end and back end teams. It also means we don't have any Java client libraries anymore, because as I said, there's no specific code to call to these individual services. And the API server is much simpler to operate. Of course, we still have the GraphQL federated gateway that we have to operate, but because there's no specific code for specific microservices, we don't need to update it all the time. So now it's just keeping the server running, basically. Now, what does that mean for our Java stack? Well, quite a bit, actually. You see that kind of that whole area where we previously required something like Rx and Hystrix, that whole area is just kind of not there anymore. We don't have these endpoints where we need to fan out to different microservices. It is not entirely true, because in the federated gateway, so if we go back a little bit, in the federated gateway here, we are actually using web client from the Spring framework. We're using web client to call out to those different microservices. However, this is completely generic code. It doesn't know specifically about any of those DGSs. It just knows how to call a GraphQL endpoint. Now, of course, web client is still reactive. So technically there is still reactive code here, but it's in a very, very specific place. And it's actually fairly simple code. It's not a lot. So we don't have other places where the reactive APIs are used like all over the place. That's a really big difference. Now, this kind of means that we just didn't have a need for using Rx and Hystrix everywhere anymore. And we have also seen that teams were very happy to kind of get rid of it, because it is really complex to write and maintain that code. As I've experienced myself, it's just not easy to deal with reactive code, just on a conceptual level. So yes, we're still using it in some very specific places where it really makes sense, but it's really not the standard anymore. The standard is really just doing GraphQL services. Now, those microservices, which we call DGSs, if they are part of the GraphQL space, they're really just normal Java apps. And they're Java apps written in Spring Boot for the most part. And we'll talk about it a bit more. However, although this architecture is a lot simpler, there's still a lot of moving pieces in place. And we are still talking about a microservices ecosystem with literally thousands of services. And that means that observability is really, really critical. There's no way you could operate an architecture like this if you don't have your observability story really figured out. I've also mentioned microservices like all the time during this presentation. And Netflix was one of the first companies that really made the microservices term like popular. And a lot of folks kind of looked at Netflix and were like, oh, if Netflix is doing microservices, that means that it needs to be true, needs to be good. And a lot of people decided, oh, if they are doing it, we need to do it. And that doesn't always make sense. So what is definitely true is that a microservice is basically owning a specific functionality or data set. However, that functionality might be quite a big space. Think about movie metadata in Netflix. There's a lot of data that goes into that. It's not just like some very small service that just has whatever movie titles or something like that. This is actually a very complex system. What is true, and that is kind of how you can start to see how to choose what to put in a separate service, is that a microservice is always owned by a single team. And in most cases, each team owns several microservices. And typically you don't want a microservice where you have multiple teams working on that service. A team should be responsible for a microservice, and they should be able to just evolve that service themselves, release it, deploy it, etc., whenever they are ready for it. So all these services should be able, for the most part, to be rolled out and deployed individually without affecting others. However, don't be fooled by the size of micro and microservices. A lot of folks ran away with the idea of microservices, where microservices should be like a handful lines of code, and it was all like super small and super fast to deploy, etc. That is really not the truth for us. A lot of these microservices that I see at Netflix are larger than like the monolith that some businesses run their whole business on. And there's like whole teams dedicated to just running one microservice, and that might be 5-6 people responsible for such a service. So yes, it is extremely important that we have this architecture, and there's no other way we could scale the number of engineers working on like the larger system. But these systems are all individually pretty sizable chunks of code to maintain. So for anyone else like looking at this and wondering, should we use microservices for our architecture? It really comes down to the question of, do you have multiple teams? If you have like a bunch of different teams, it is a very good thing if each team can own a individual part of a system, of a larger system, that they can like evolve and work on and deploy like isolated from the other parts of the larger system. That is the most important part. If you are a small team of engineers, like let's say you have like 5-6 people in your team, and that's it, and that's most companies that I've worked for in the past before Netflix, microservices just don't make a lot of sense. And you should think really hard about introducing all the complexity that comes with microservices, and mostly because of the remote nature of microservices, before you kind of dive into that. So at least keep in mind kind of the size of these services that we are thinking about here. Right, so now that we've talked about microservices, how are they actually implemented? And let's start to deep dive into our Java stack. So right now, we are very well on the way of mostly running on Java 17. And this is really, really good news, because last time I gave this presentation, we were still mostly on Java 8, and that's not actually that long ago, and it was a little bit embarrassing. Now, there was a good reason that we were still in Java 8, because we had built this whole application server framework. That's kind of before we started using Spring Boot, but we still had a lot of code in that framework that was using like older versions of Jersey and Juice. And it was actually really hard to upgrade those services to newer versions than Java 8, because there were just a lot of instances in the JVM that affected those lower level libraries. So we had to take care of basically fixing those issues and then start moving forward. The other reason that service owners were kind of reluctant to update to Java 17 is that they didn't really see the benefits of doing so, because there are some new language features, and they're definitely interesting looking at Java 17. But in the versions before Java 17, there really wasn't that much going on. There was a lot of like foundational work being done in the JVM itself to pave the way for a better future. But just from language features, it wasn't really that much. It wasn't that big of a deal for service owners. But it is definitely changing. Like the Java versions that are coming up, they are super interesting when it comes to Java features or language features. The JVM that we're using is just a JVM from Azul, so it's an OpenJDK build, and we don't do anything else on top of that ourselves. This is kind of funny. About a year ago, our JVM team, they put up a job post, a job opening, and people kind of misread that's the description of the job, and they started like this thing like, oh, Netflix is running their own JVM, they're building their own JVM, and some companies in the past have done that, but that's actually not the case. Netflix is not running our own JVM. We are just running an out-of-the-box OpenJDK build, and that is exactly what we need. Just to get an idea of kind of the scale or size of the Java ecosystem, we have about 2,800 Java applications. These are all like backend applications for the most part, and some like stream processing jobs. And then about 1,500 internal Java libraries. And these are often like client libraries that add maybe some caching and things like that. For our build system, we use Gradle exclusively. And on top of Gradle, we have a set of Gradle plugins, which are all in Nebula, which for the most part is all open source. I'll talk a little bit more about that. And for the IDE, we use pretty much exclusively IntelliJ. Although there is no rule that you have to use IntelliJ, that is pretty much what everyone is using. Now, I was talking about JDK 17 a bit just now. And something that we found while upgrading to Java 17 is there was a massive performance improvement just updating from Java 8 to Java 17. And we have seen about 20% better performance updating service to Java 17. And for the most part, that's all related to garbage collection. There's been a lot of work done in improving the garbage collection in the different Java versions leading up to JDK 17. And what we found, and we've seen the same from others, is that 20% is something you basically just get for free. You don't need to make any tuning changes or code changes. This is just something that you get completely out of the box, and that is obviously very significant. If you run like workloads at a cluster sizes, etc., that we run, 20% represents quite a bit of money. For the most part, we are using the G1 garbage collector for most workloads, and we have found this is the best balanced garbage collector for like your typical microservice. We've definitely done a lot of experimentation with the other garbage collectors that are available now. And for example, Zool is running Shenandoah as the garbage collector. And these different garbage collectors basically just have different trade-offs that you get. So there's some pros, there's some cons, and that might be better for specific workloads. But in general, we find G1 to be like the best mix of things. But again, this performance improvement alone should be a very good reason for everyone to put the work into to upgrade to JDK 17. Now, the other thing that I mentioned is that we're using Gradle for dependency management with the Nebula plugins. And the most important thing that we do with Nebula is that we have dependency locking. And I want to talk a little bit more about that because I think that is something that others should consider as well. Now, we all know that Java has a flat class path. And it basically means you can only have one version of a jar file or a class on the class path. Only one of them will be loaded. Now, let's dive into this issue a little bit. Let's say that we have an application, and in my application code, I'm using version 2.0 of AwesomeLib. And version 2 of AwesomeLib has a class A, and in class A, we have two methods. We have a say hello method, and the say hello method in this version has two method arguments. Now, we also have the 1.8 version of this library. And I'm not even using this version directly. I'm just transitively pulling this in through some other library that I'm using. And it is, if you have a fairly complex application with like a lot of dependencies, which is very common, you will run into this sooner or later. So version 1.8 of this library also has two methods, but it only has a single method argument for say hello. You might argue, well, that was a really bad choice by the library owner, and that's probably true. But this is just the reality of what it is, and it's really not uncommon. Now, it gets even worse because in version 1.5 of the library, we only had a one method. We didn't have the do something method, which this was introduced in 1.8. Now, you would say, let's say, backwards compatible change, right? You just added something, you didn't remove anything. Now, given this picture with these libraries, if I call the do something method from my application code, what is going to happen? Nobody knows. We'll find out at runtime. So, because the class path is just flat, the JVM is just going to load whatever class it happens to find first on the class path. Now, if that happens to be version 1.5, because that's how it's happened to be on the file system, we will get a no such method exception, because as we have seen in AwesomeLib version 1.5, this method just didn't exist. It was introduced in a later version. This is, of course, a problem that we're all familiar with, and it's really painful to deal with. So what we need to do is we need to select one version that we want to use consistently. And then we want to make sure that we are always using that one version every time we build the application. And this is where Nebula comes in. And this is, again, something that you can use. This is all open sourced. Actually, in Core Gradle, they have taken some of these concepts more recently and kind of support this same thing. So you can either get it with Core Gradle or with Nebula. And what this command does is basically it writes a dependency log file, and that is basically a long list of all the versions of the dependencies that we resolve to. And Nebula will pick the best version out of those 3 versions that we had. And the best version is typically the newest version, assuming it's backwards compatible. That's not always the case. And if we as a user know that we need a specific other version, we can fix that version. But it will make sure that all those transitive dependencies that we pull are all using the same version in the end. Now, there's no guarantee that it will actually work, but at least now we have the one version to worry about. And every time we build, it will use exactly that version. If we want to update our libraries, we just generate a new log, and that is a separate commit that we have, and that is when we pull in new libraries. Now, with that fast-moving ecosystem of libraries and library updates at Netflix, with those 1,500 libraries that we have, libraries pretty much just change all the time, and typically once a day, every service will automatically run this dependency log mechanism, pull new libraries, commit that if the build are still working, and that is kind of how we are always using the latest version of all our libraries. But when it fails, we at least can very easily track back where issues might have been introduced. So this concept of dependency logging is definitely something I recommend looking into. Now, most services today are all based on Spring Boot. And on top of Spring Boot, we have actually built our own framework called Spring Boot Netflix. And this is basically, we basically provide a whole bunch of auto configurations on top of Spring Boot. So it's just the normal extension mechanism that Spring Boot provides to add features that are important for the Netflix ecosystem. So our developers are mostly just using Spring Boot. But on top of that, they get support for gRPC clients and servers. We integrate with our security stack, so the authentication, authorization systems that we have. At Netflix, we have our own systems in place for distributed tracing and metrics and logging and all these things. So that's all coming out of the box. We have mechanisms for remote configuration so that you can reconfigure your services basically while they're running. Service discovery is part of it. We have a set of HTTP clients. These are pretty much the HTTP clients that you know, like web client. But then on top of that, we have added integration again with observability and things like MTLS that we require. Then there's all sorts of data stores that we need to integrate with, like we have our versions of Kafka and Cassandra. And this all just gets deployed with embedded Tomcat, as you would probably do yourself if you use Spring Boot. So as I said, these extensions are basically all just auto configurations, and that is basically how we build our version of Spring Boot that really fits well in the Netflix ecosystem. But primarily, what you see as a developer is just Spring Boot. Now, you might be wondering why Spring Boot. Well, if you're on this stream, you might be a little bit biased already. But Spring Boot is pretty much the most popular Java framework. So that means there's a lot of resources out there that we can leverage. There's, of course, the very active open source community and the really awesome Spring team that's kind of leading that. There is a lot of existing documentation and training and all these things. So that makes it much easier for us to like train our developers as well. But I think the most important thing is that the Spring framework has just been very well maintained over the years. And I'm not just talking about Spring Boot. I'm talking about the Spring framework and its ecosystem as a whole. I think I started using the Spring framework probably 15, maybe more years ago. And if you really look at how things are put together, it is still using the same concepts. And of course, a lot of things have been improved and changed, especially with Spring Boot. But they have done a really amazing job in following the same concepts and be really good at backwards compatibility as well. And that is important for us for the long term, because we don't want to be switching to like a new framework every 2 years. That is just way too expensive. So even if there might be other frameworks that you could be excited about because they have these whatever specific features that you are looking at, this longevity of a framework is really what matters here. And of course, recently Spring Boot 3 was introduced, and we're right in the middle of making that upgrade happen, and that's probably going to take some time. Now, I personally, I'm super excited about this upgrade. If you look at the feature set of Spring Boot 3, it is actually really not that exciting. There's not a lot there. But what is exciting and what we kind of unlock with Spring Boot 3 is that the Java ecosystem, like as a whole, is finally moving at a really fast pace again. Spring Boot 3 is baselining on Java 17. And because the Spring framework is such an important framework in the larger community, what we see is that a lot of other libraries are now also bumping to Java 17. So now finally, the whole ecosystem is starting to leverage those newer Java versions with all the benefits that we get from that. And that is also unlocking the doors to start using features that are coming in even newer Java versions, like Project Loom, that is coming up in the next few Java releases. And that's where the really exciting things are coming. But Spring Boot 3 is basically responsible for unblocking like the way for the whole ecosystem to start moving forward, because it's so impactful. It also means that my team has a lot of work to do, because there's code changes that need to be made on our outer configurations. That's not that big of a deal because it's just our teams. But then there's also the new outer configuration format. That means that all our libraries that integrate with Spring needs to be updated. We have the JavaX to Jakarta change to deal with. Now that's of course not Spring's fault. This is just something that happened in the larger Java community, but it is something that we all have to deal with. And we did invest in an open source, contribute to an open source plugin, which is the Jakarta plugin, which is basically a Gradle plugin that helps transforming libraries from JavaX to Jakarta. So if you're kind of looking at this migration yourself, that might definitely be a tool to look into, because this makes it possible to use libraries that are still using JavaX in like a Spring Boot 3 environment. Then in Spring Boot 3, there's also the revamped observability. That all looks a lot better, but it also means that we need to make a lot of changes there. And a change that is kind of impactful for us as well is all the changes around Spring Cloud AWS, like the way you interact with SQS, for example. There's quite a few changes there. The whole project has moved as well, so that actually requires quite a few changes in a lot of applications for us as well. So in the next months, we're starting these upgrades where we have the first services running on Spring Boot 3 already, and we're now investing in tooling basically to make this upgrade as easy as possible for our application owners, because again, we have 2,800 applications running on Spring, and they all need to make that upgrade. So that's a lot of work. If you're just looking at your own one service that you need to upgrade, it's really not that big of a deal, and I recommend to just do that as soon as possible. And then, of course, we talked about DGS and GraphQL, and we are using the DGS framework that we open sourced probably 2-3 years ago now. And this integrates deeply with Spring Boot, and it basically gives you a annotation-based programming model to create GraphQL services. So if you're looking at GraphQL, this is definitely something that I recommend. Of course, Spring Boot also recently introduced GraphQL support. That's not something that we are using because we heavily invested in the DGS framework. I guess there's benefits to both, but the DGS framework is definitely what we are using and will continue using in the future. One thing that you also get there is that you get code generation with like a Gradle plugin. That helps a lot, and we have support for GraphQL Federation out of the box, and that is obviously very important for our architecture that is all now based on Federation. Right. Then looking into the future, what else are we excited about? Well, it is just a super short list. First of all, we're, as I said, in the middle of this Spring Boot 3 migration. That is going to be pretty impactful, especially because it now unlocks the whole Java ecosystem that we have to start using new language features and things like that. So we are well on the way to be baselining on Java 17 ourselves. And again, more importantly, the future Java versions. So we already have a bunch of services running on Java 19 and 20. And then I'm really looking forward to Project Loom, which is coming in the next few Java releases. Like different parts of it will be coming in the next Java releases. And I think that is really going to change the way we are thinking about how to deal with parallel code and also scaling our services. It will make it a lot easier to do that kind of fan out work that we talked about. And for a large part, I think for a large part, it will kind of eliminate the need for a lot of reactive code that we might still have. So that's going to be a super interesting one. Let's see. That brings me to the end, and I also see there is some questions that I haven't seen yet.
Yeah, we do have a couple of questions. Let's pull them up. First of all, Prashanth is watching on LinkedIn, and he says, how do we handle service failures in this new architecture?
Very similar as we have done in the past. So let's assume that, actually, let me bring up the relevant slide for this. Let's go back to this new architecture right there. Let's say that in this case, the images DGS has some sort of problem going on. They just rolled out a new deployment. They messed up, and it is failing. Now, what happens here in the GraphQL Federated Gateway is that we have very aggressive timeouts going on. So let's say the images DGS is not responding within that very aggressive timeout. It will actually just fall back with just the titles of the shows, because we had a query with titles and artwork URL. Artwork URL can't be loaded, so we just get back titles and an error message that the UIs can then react on, basically.
I also heard you mention caching in the API server. Did that carry over into the GraphQL Federated Gateway? Is there caching layer in there?
So most of the caching would be happening in the actual DGSs themselves. So in most cases, instead of, let's say, talk to a Cassandra database, it might read from in-memory cache. And that is where we get most of the benefits. The federated gateway itself, there's some caching logic there, but that is fairly limited because we don't want to have any specific knowledge or code there about specific backends.
Another question from Brian on YouTube. What repo types do you guys use? Mono repos, or is there a repo per individual service?
Yeah, it's kind of weird. So we use individual repositories for each and every project, so every service and every library. But then the thing that kind of sort of makes it almost feel like a mono repo without it being a mono repo is that, as I said, with the dependency locking process, a service is basically always using the latest version of all libraries at any given time. So you are always running on the latest code of whatever other teams provide, but it is technically not a mono repo. So this is only kind of your dependencies that you have.
That question ended up being a really, really interesting nugget from that answer. So, Brian, thank you for asking that question, and thanks for the answer. This session has been way beyond what I expected. You've given us such a good overview of not going into language details, but like the steps along the way has been wonderful. I literally have goosebumps under my hoodie here. And you're hitting a lot of like the main points, at least from my journey, like, hey, I needed to make this decision. Do I just jump when there's a new framework, there's a new feature? Do I jump? No. There's kind of a process. First things first, you've evolved continuously. You gave us a great background of kind of the journey, and you kind of, I felt like we got a really good inside look at what's going on today. One more question here from Fabio. So all microservice communications via gRPC, no use of Kafka. I think I saw Kafka and Rabbit on there. You want to touch on that?
Yeah, we have lots of different ways to communicate between services. And the fact that we have so many different options isn't necessarily good. It is somewhat coming with the fact that, well, you have different tools for different jobs. So that's definitely the case. Then teams also have a lot of freedom in choosing their own, like the technology they want to use. The downside of that is that we end up with a lot of different technologies that might be competing with each other. But yeah, for communication, we have there's actually a lot of just HTTP calls. For example, the communication between the GraphQL gateway and the DGSs, that's just all HTTP. It's basically an HTTP call to a GraphQL endpoint. There is a lot of gRPC use for service-to-service communication. That's kind of the primary technology there. Then for like more messaging-based systems, we have Kafka. That's kind of our primary system for that. But we also have a lot of teams using SQS from Amazon, kind of depending on the requirements there. So yeah, these are all things that are actively being used.
Excellent. Another question here from Gennady. Solving issues. This as we're moving Java 9, did you ever jump? And I'm going to take a guess. I'm going to guess that you probably faced that issue in one of the thousands of applications along the way. Did you have any insight into where Java modules might have been used or not?
So this is reset because as I showed in one of the first slides, I actually wrote a book about Java 9 modules. So I kind of know about it. I'm kind of excited about it, but no, we're not using it. And realistically, we're never going to use it. The biggest problem, I guess, with the module system is that you can only have like one version of a jar on a class path, and that is technically a really good thing. That is exactly what you want, but it's also really hard to actually achieve that if you have a complex class path with lots of transitive dependencies. And on top of that, things like split packages, which is also like a bad thing to do, right? It's a code smell, but it's also the reality of a lot of existing libraries that we have in use. And these are kind of just big blockers to not be able to use the module system.
Will you do me a favor? Will you pull up the slide that has your book on it? I mean, let's give it a shout out. If we've got audience that's looking at Java modules or facing issues with Java modules, let's point them in the right direction. Thank you so much.
So
Man,
I've always been like super excited about modularity. So the one thing that I do need to say is also sort of reducing the need to use something like the module system. Gradle has done an amazing job in the last few years to get a lot of benefits from like modular design and modular architecture without necessarily requiring a runtime that is modular. So what they have done, they have introduced, if you declare dependencies, you can make the difference between an API dependency and an implementation dependency. And an API dependency is a dependency where you want to expose the APIs from the dependency to your users. Well, an implementation dependency is kind of what the name says. It's just an implementation detail of your library. Now, that sounds like trivial on paper, but that actually makes it possible to write completely modular code with most of the benefits that you would get from a module system, but at build time. And that solves a large part of this whole equation. So if you're using Gradle, that's definitely something you can leverage.
We have somebody, shouting your praise. You have Pluralsight courses, and they're advertising for you. That's wonderful. Benjamin, one of our regulars here, says, "Can I get a copy of these slides?" Benjamin, I took snapshots of a bunch of the slides. They're on a Twitter thread, so you can go there for sure. I'll see if maybe we can make those slides available offline.
Yeah, so one correction, I'm actually not on Pluralsight. Pluralsight is awesome. They might be confused with Sander. I'm good friends with Sander, and as you can see here, he was the co-author of the Java 9 modularity book. He really knows his stuff. So yes, these are definitely courses on Pluralsight that I would recommend, but I can't take any credit for it.
Excellent, Paul. I've been lucky enough to have met you before today, and we're doing some really interesting things. I love the overview that you gave us. And one of the things we talked on, I know I've got an ancient device over in the other room that is still working, right? Hitting those ancient APIs, multiple years old, and just the challenges. I think about all the customers and people that I deal with and the problems that they're facing. And you've given us a really good explanation of why you made the decisions, when you made the decisions. And I think you gave us a great journey along making those decisions. So thank you so much for this session. It was, again, exceeded my expectations, and I think it's super valuable. But yeah, those are the questions that I had. This has been awesome. Again, thank you so much. We had great questions. We had people from all over. This is the most live attendees of any session that I've hosted so far. And I'm sure that we're going to get a lot of repeat views. Again, this is just a masterclass. I am so thankful. So I'm going to wrap it up here. We have a few things coming up. We've got our VMware Spring Academy available online if you want to learn more about Spring. This is an easy place to go. Go dig in, get all the stuff you need for your prep courses. There's a free option. There's a paid option. Take a look at spring.academy. Also, we want to see you at VMware Explorer and Spring One coming up in August. Thank you, everybody, so much for joining us today. This has been a wonderful session. Thanks again, Paul. I look forward to hearing from you again, hearing your journey to Spring Boot 3, and I hope to see you at Spring One as well. Thanks, everybody. We'll see you next time.